I do not think I have to point out which grade this is or which subject, nor which chapter or section. So, obviously, before we start on talking about chemistry or anything really, we need to define what it is first. So, well, chemistry is the study of matter. Now, it's anything that has mass and takes up space. Okay, so what can you think of that has mass but doesn't take up space? Nothing. So, chemistry is technically the study of all things. Well, except light, because that doesn't take up space, but it also, in theory, does not have mass. It has relativistic mass, but that's for physics. So chemistry is a study of almost all things, all tangible things, at least. Now, of course, other definitions may be the study of interactions and reactions of particles. Why interactions and reactions? Well, if it's just interactions, such as particles bouncing off each other, what is that? And say this one's going this way, and they end up bouncing off each other. Well, that's physics. And, I mean, if you say what makes food change as it's cooked, well, you can guess why it's correct, also correct. Now, of course, there are many other things that all fall under chemistry. For example, photosynthesis, the basis of all life on Earth. Well, almost all life, because there are a few bacteria that do chemosynthesis and all that stuff. But photosynthesis, for example, wait a second, that's a chemical process. I mean, we're rearranging atoms, right? Inside molecules. But of course, technically I'm a biology major, so we biologists like to keep that in our territory. Now, many people have said that biology is applied chemistry, and yes, this is true, but biology also has applied math and applied physics in it. That's why biology is not considered just a sub-branch of chemistry. Now, chemists say that they are the central science, just like physicists say they are the central science, and mathematicians say that they are the foundations of everything. Of course, chemistry is often called applied physics. Why is this? Well, if you are rearranging atoms and stuff, so say you go from this to this. Well, what sort of processes have to happen? Energy transfers, right? Well, if there's energy transfer, it's a physical process. So that's physics, isn't it? So that's why sometimes people say that chemistry is applied physics. Now, all you really have to care about is chemistry is the stuff you are about to learn. You don't need to be engaged in this glorified philosophy contest. Now, of course, speaking of philosophy, before we can study anything, we have to talk about how science works. Now, science is not like philosophy. Philosophy is like, oh, we construct an idea of how the world works, and we say that, oh, it must be so. No. Aristotle got in the way of science for thousands of years with his imagination. So empirical knowledge is gained through experimentation. What's theoretical knowledge? Well, this is what you think of to explain what you found in your experiments. So experiments lead to theories. This is not a chicken or egg problem for the most part. I mean, occasionally, yes, you are going to propose a theory and then test it, but for the most part, you experiment and then you propose a full theory. Why? Because science is not like everyday life, where theory means you take a guess. That would be a hypothesis. A hypothesis is a guess. For example, say you have a flashlight or a calculator, and it doesn't work anymore. Now, there's two guesses that you can make. One is that the screen is broken, The other one is that the battery is dead. Of course, the third one is that the calculator itself is broken somehow, like inside. The processors are fried or something. So, to test these, you experiment by replacing the battery. And there are two outcomes it can produce. One is that the calculator works again, so it confirms that your theory is going to end up being the calculator's battery was dead. And the other outcome is that it doesn't work again, which means this can feed back on itself. It can also feed back to the hypothesis. Theories can lead to hypotheses in a more indirect manner. But the point is, in science, a theory is comprehensive and it's an explanation or model based on observation, experimentation, and reasoning. So no, evolution is not just a theory. And if you choose to believe that it is just a theory, then honestly, you will not get very far in most universities, most serious universities at least. Now let's talk about some everyday chemistry. So what do you observe every day that's about chemistry? Well, I believe there was a poem about sailors lost at sea. Water, water everywhere, but not a drop to drink. Here we have chemistry. Chemistry. Everywhere. Well, everything you see is a product of chemistry, even biological things. I mean, your food, that came from photosynthesis and other reactions. So, that's chemistry. The only problem that we have now is, what's the but not a thing? But sometimes this quote is used without that part. For example, I remember a meme using a screenshot from, I think, Toy Story or something, one of those movies, and they were good movies, and it was something about, like, ponies everywhere or something. While your hand was clapped around the other guy's shoulders. So, of course, the toys represented in that movie are also products of chemistry. Now, these are probably a little bit harder to identify. Well, okay, so this and this are harder to identify. If you can't identify this thing, well, you probably have larger problems. So the point is, okay, this is a soccer ball. This resembles what you would get if you took the frame of a soccer ball and made it all straight lines instead of kind of bent like on an actual soccer ball. So what's this? Well, these are fullerene molecules. You've probably heard of C60. C60. Now, this is 60 carbon atoms joined together in a structure that looks like this, except of course it's on an actual molecular scale. And you might be thinking, hey wait, I heard C60 was supposed to be balls, and why are there so many clumps? Well, nothing says these particles can't stick to each other, so you end up with clumps, and you end up with more smaller clumps. Now, why do we not actually see any individual particles, or molecules rather? Because they're too small to be visible. Now, it is not recommended to mix C60 with mineral oil or other oils. Why is this? Well, that's one of the most slippery, i.e. low coefficient of friction, solutions that you could possibly make. Although I would not recommend it for pranks or other similar lubricant duties. Why do you think that might be? Oh yes, C60 is somewhat expensive. So instead, if you're going to try to prank somebody, like play a joke on somebody, you should use oil and water instead. Why? Because the chemical properties of those make sure that they don't mix, and the emulsion, which is the term we use for the suspension after you stir it in well enough, what happens when you step on it? Well, you know how the cartoons have banana peels and they're all slippery and stuff? While that is not oil and water, it has nothing on oil and water. Oil and water is much more slippery than banana peels. Oh, and why are banana peels slippery? Well, the fluid that comes out when you crush them, mostly cellular fluids, behaves kind of like mucus. So what's mucus? Well, you are welcome to take a finger and do some excavation up your nose, and you will find mucus. Now, saliva is technically also a kind of mucus, according to some people. Why? Because it's secreted from a mucous membrane, and it's used to keep the mucous membrane, i.e. the inside of your mouth, moist, and therefore not let it dry out. Of course, what does saliva do to starch molecules? Well, saliva contains certain enzymes, salivary amylase, that digest starch. And what is this? Well, while it's a process that's talked about in biology, it's also a chemical process. So you are welcome to go take a piece of bread, put it in your mouth, and wait a little bit, and it will taste sweet, because your amylase has chopped up the starch into maltose molecules. Now, what next? Oh yes, right, so the guy's in charge. Now, they call it the International Union of Pure and Applied Chemistry and the Scientific Community. Well, technically, the IUPAC is just this first part. But the scientific community is governed by IUPAC when it comes to chemistry. Somewhat when it comes to biology. Why do you think that might be the case? Because biology is, in large part, applied chemistry. So when they discover a new chemical compound, they still have to run it by IUPAC, more often than not. Now, IUPAC decides on naming conventions. So the naming conventions you will be learning, eventually, are all because of these guys. Now, you might dislike these guys strongly by the point that this course is over, but remember that it's easier than the haphazard naming of, say, water, ammonia, urea, and all of these other household chemicals that you deal with regularly. What's urea? Well, it's in urine, so when you pee. And what's ammonia? Well, it's a breakdown product of urea. But does that actually tell us what ammonia is? Can we take the name and dissect it and somehow come up with the chemical formula? No. Water? No. On the other hand, dihydrogen monoxide? Yes. Why is it then that water, ammonia, and urea and these terms are still in use? They've been grandfathered in because they are in such common use that, well, to replace them would just be tedious. Can you imagine reading a food label that says ingredients, dihydrogen monoxide, and then some other chemical that takes an incredibly long name? Because guess it, believe it or not, high fructose corn syrup, which is what is one of the leading causes of diabetes and one of the leading sweeteners used in the US and Canada, at least. Well, that stuff, yeah, fructose means that you are going to end up with quite a large name if you didn't just go with fructose. Of course, you are welcome to eventually try it once we finish our naming convention stuff. Now, the stuff that will be advanced enough to name that is probably going to be later than grade 11. But for now, let's proceed. So in summary, chemistry is the study of matter and its interactions. And like all studies, it's a process for acquiring knowledge. Now, chemistry involves experimenting in the macroscopic world and the microscopic world. Now, how do we conduct experiments in the microscopic world? Well, this is a more recent development, by the way. For the most part, we still just theorize about it after doing macroscopic experiments. However, in more recent times, they've been doing little silicon chips, labs on a chip. So they're like little silicon chips where you have little things, little chambers, and these are electrically governed so that they can connect together as needed. So these are very complicated, and this is a very crude drawing of one, of the general idea. But the point is that microscopic chemistry is now a reality, even though we still mostly stick to macroscopic. Why? Because these things are not that easy to handle, and also not that easy to clean. And they're also rather expensive. So why bother? And also, the yields for many reactions are so low in percentage that after you get your product out, unless you start off with a relatively large amount of reactants, you are not going to get enough out to be really useful. Why? Because if you're measuring melting point, even though the melting point measuring apparatuses usually have a little magnifying scope for you, it's still hard to tell when you don't have enough to actually see under that scope. So, the interplay between empirical and theoretical knowledge is critical in the study of chemistry. Well, it's critical in all sciences, technically, but more so, it's more obvious in chemistry and biology. Why? Because in physics, when you are doing experiments, they tend to be a little bit more complicated these days. Why? Think about it for a second. Well, in chemistry, you're combining all sorts of different molecules. So there's lots of different experiments that could be done. But in physics, well, okay, we have Newtonian mechanics, we have Einsteinian physics, and, well, we have quantum physics. So quantum physics is high-level stuff, and they won't let you do very many exciting new experiments for a very long time. So that's why the empirical and theoretical knowledge interplay is not as obvious in physics. You're mostly going to be stuck there doing paperwork. Now, the International Union of Pure and Applied Chemistry, IUPAC, sets rules and standards for chemists worldwide. These include naming conventions, general safety regulations, and so on. Now that we've talked about the basics of somewhat of what chemistry actually is, that's it for this section. And hopefully you will go and enjoy a glass of water or something. And while you're doing so, you will think of how that is all about chemistry.